Welcome. My name is Donna Atanasio, and I lead the energy program here at GW Law School. Our next panel will be addressing the supply chain related challenges that are faced by advanced nuclear technologies. It will be moderated by Dan Stenger. Dan is a partner in the law firm of Hogan Lovells in Washington, D.C. He specializes in nuclear energy matters and practices before the Nuclear Regulatory Commission. Dan is also an alumnus of GW Law School and has been a staunch supporter of the Sustainable Energy Initiative since its inception. It gives me great pleasure to welcome Dan and the panel. Thank you.
I presume everybody can hear me. If not, please raise your hand. So I hope the audio is okay. So this is the panel on the supply chain of the future for nuclear energy. I'm Dan Stenger from Hogan Lovells. I'm a GW Law School graduate. I graduated a few years before Kathleen Oprea, who spoke this morning. I graduated in 1980, and I've been doing nuclear energy law for around 40 years now. And I must say, this is really about the most exciting time for nuclear energy ever. We're at this precipice, as Dr. Huff put it, I think, about that nuclear energy is recognized widely as part of the solution for climate change concerns. And to get to some of the projections of net zero, I've seen estimates that indicate we need a new 90 gigawatts of nuclear energy, which is essentially replicating the current fleet of operating reactors. As Steve Burns talked about yesterday, we have 93 operating reactors in the United States. And the supply chain to support new nuclear energy is really a key issue. You'll hear from our panel today about the importance of, and really the need to rebuild the supply chain for nuclear energy that is to some extent dwindled over the years in order to support commercialization of nuclear energy. And we really have the best panel possible to talk about those challenges and potential solutions. I would emphasize another point too, that we heard yesterday from Fiona Riley, a lot about the importance of the contracting structure for nuclear projects. And you will hear from our panel today about the importance of making sure the contractual incentives for all participants are aligned to achieve success with the project, and how some of the projects around the world, you could cite Kyoto in Finland and Flamanville in France, and even Vogtle here in the United States, Vogtle 3 and 4, where there have been real challenges with project execution. The reason I highlight that for the lawyers on the call and also any students on the call is it's really the lawyers have a very important job here in setting up these projects to success. The contract structure and contractual incentives are going to be essential for the success of these projects. So this is a very exciting time for nuclear energy developers, as well as lawyers who practice in this area. So with that, I really want to move forward to turn this over to our panelists. We have just a great panel today. We're going to begin with Creighton Geppel, who is Senior Vice President and General Counsel for TerraPower. For those who don't know, TerraPower was founded by Bill Gates. Bill Gates' Advanced Nuclear Reactor Company. We'll then have Dr. Robert Ledoux, who is a Program Director at the Advanced Research Projects Agency, Energy, affectionately known as ARPA-E. And Bob will talk a bit about what ARPA-E is, but for those who don't know, it's a very exciting organization, and it's well worth researching. We also have Dr. Andrew Souder, who's a Senior Technical Executive at the Electric Power Research Institute, EPRI, who'll be able to talk about some of the research and programs EPRI has underway to support new nuclear development. So with that, I'd like to turn it over to our panelists for their presentations, which will be around 5 to 8 minutes each, and then we will have a good amount of time for questions and answers. So Creighton, please take it away.
So thank you for the kind introduction. And as a proud father of a GW alumni, I wanted to thank um, Professor Adanasio and GW Law School for putting on this seminar today. My name is Creighton Geppel, and as the General Counsel of TerraPower, I want to do really two things during today's short session. First, I want to introduce you to the Natrium Reactor that TerraPower is developing. And second, I want to tell you a little bit about supply chain challenges that we and others face in bringing to market first of a kind technology. Um, let's see, let me move to the next slide. So TerraPower's flagship technology is our Natrium Reactor, which is a sodium cooled fast reactor. And one of the things we did is we incorporated thermal storage, which allows the Natrium Reactor, which has a power output of 345 megawatts electric, to flex up to 500 megawatts electric when needed. Our Natrium reactor benefits from a strong public-private partnership that we have with DOE under a multi-year advanced reactor demonstration project award. And as part of that award, DOE is providing approximately $2 billion of funding, and TerraPower and its partners are matching that funding with private funding dollar for dollar. One of the things that we did with the Natrium reactor is we really reimagined what a nuclear reactor would look like. And we tried to limit sprawl. The entire plant size is approximately 44 acres, with a nuclear island being about 16 acres of that. And also complexity. We tried to minimize that. Another innovative thing we did was add the thermal salt storage feature, which should help Natrium integrate with the variability of renewables. This could allow utilities in states like California to deal with problems they're already facing with managing renewables and the variability that they introduce into the grid. You know, the magnitude of this kind of challenge was recently illustrated by the fact that California Governor Newsom is now seeking to potentially delay the shutdown of the Diablo Canyon reactor in California. One significant design innovation that we made with a Natrium reactor is what we refer to as decoupling, which is the separation of the nuclear island, which you can see in the lower left here, from the energy island. This not only provides the kind of operating flexibility that I mentioned and the ability to deliver more power at peak demand times, but it should also help the Natrium be more cost effective to build, because the energy island will not have to meet some of the more exacting and expensive nuclear quality standards required for the nuclear island. Another exciting feature of our Natrium reactor is our siting planning. And we plan to site it at a former coal plant in Kemmerer, Wyoming. And we have a lot of local and state support for this siting in Kemmerer, because it's really a very tangible example of the green energy transition that so many have been talking about. And you know, as mentioned, you know, one of the benefits of our design is that the energy island, we've opted to use many storage technologies that have been proven in the concentrated solar space. We're hoping that this will substantially reduce the costs and complexity for that portion of the Natrium reactor supply chain. But there are also challenges too. You know, in many cases, we're finding that we need to not only design and build the new Natrium demonstration reactor, but also that we have to help reestablish the U.S. supply chain. And this is a really exciting area, I think, on the contracting side in terms of contract structure. One of the things I like to say is that in addition to the innovation that needs to happen on the technical side to bring new advanced reactor technologies to market, we're going to have to equally innovate when it comes to contracting structures and commercial structures in order to succeed in this process. One other thing that is a thing that we're going to have to work through too is, some of the constraints that exist in our in our DOE award in connection with supply chain, because we're operating under a U.S. award, and so obviously there's a strong interest from a policy standpoint to try and make sure that that supply chain development happens in the U.S. But there are going to be some circumstances where we're going to need to look to try and leverage foreign capabilities from friendly partner nations. And to date, I'd have to say that DOE has been a really good partner, as we've looked at early discussions in that area. It's going the wrong way, sorry. One other thing that I wanted to highlight as a challenge, and this is kind of a good example of the need to reestablish the supply chain, is the whole situation around uranium enrichment and deconversion. And I think the Russian invasion of Ukraine was a kind of wake-up call for the entire nuclear industry. And currently, about 20% of enrichment and deconversion for even the existing light water reactors comes from Russia. And the challenges of this are even more acute in the context of advanced reactors like our Natrium reactor and pretty much all of the other advanced reactor demonstration program awardees that are developing new technology, which require HALEU, or high assay low enriched uranium, which is enriched to between 10 and 20%. At the end of 2021, DOE issued a request for information as a first step toward getting HALEU production developed here in the U.S. The only current location where this material is available from is Russia, which is obviously extremely problematic at this point. We're hoping that that there will be a follow-on DOE program with strong congressional support and appropriations, coupled with private industry demand from TerraPower and others, which will quickly make HALEU available in the U.S. The costs, is noted here, will be substantial for developing this new kind of capability. Could be more than $500 million for enrichment and deconversion. And I think, this really underscores, part of the challenge that we face, because we and others face, just because, at the same time as we're working on developing and bringing to market the new technology, we also have to reinvigorate, together with the U.S. government, the whole supply chain needed to support this industry. And last, I just wanted to show you the link to, if you want to receive more information on our Natrium reactor technology. And that's it.
Thank you, Creighton. Bob, would you like to go next?
Yeah, I'm going to try to share my screen here. Tell me if you see my screen.
Yes.
Is it in, putting it in presentation mode? Do you see the correct one?
Yes.
Okay, great.
We've got it. Great.
Technology works sometimes.
Success.
Thank you very much for that introduction and the opportunity for the organizers to let me say a few words about Opry's efforts in supporting advanced nuclear R&D, that's our game, and also the future supply chain, which is the topic here today. So just a couple words about Opry. We're the new kid in town. We're part of the Department of Energy, but we really only got some money in the bank in 2009. So we've done a lot since 2009, but we are a relatively new part of the Department of Energy. And we were stood up, obviously, to try to do high risk, high reward R&D. We're not top down driven, but we have a very specific charter. And our charter and our goal is to enhance the economic and energy security of the US through the development of energy technologies in 5 areas: reducing imports, improve efficiency, reduce emissions. It was added a couple of years ago to improve and manage the cleanup and disposal of radioactive material in nuclear fuel, and to improve the resilience, reliability, and security of the energy infrastructure. And you'll see that commercial nuclear power checks every single one of those boxes. And I'm not a lawyer, but I think we have a statutory obligation in Opry to also have a tech to market approach where we don't just develop these things, but we make a pathway that they can actually be deployed. And that goes to our second goal, was to ensure the US maintains a technological lead. And we also have an emphasis on US manufacturing, which is crucial to the supply chain. Now, there's a lot of advanced reactors. We just heard about the beautiful Natrium, but I want to point out for advanced reactors, no matter what, we couldn't rely just on our existing supply chain because they operate under different conditions: corrosive, high temperature materials, high temperature gas reactors. So Opry is part of developing new tools to be used in these, but it equally needs to develop the supply chain that can address these, growing off our experience. But I do want to point out there are very new things being built and designed here. So how did the Opry portfolio that present exists look at how we can help and contribute to advanced reactors and supply chain? So our 2 first programs, Meitner and Gemini, they concentrated, primarily was their focus, but not exclusively, on advanced reactors. The Meitner was to reduce the CapEx cost, to lower the cost of building advanced reactors and its supply chain. Gemini was more focused on digital twinning to reduce the operational expenses, but it has a significant component on advanced sensors for reactors, which is a crucial supply chain issue. The 2 newest programs, one of them is actually an active forward cure I can't speak much about, but the Onwards program tried to acknowledge really a key gap in both development as well as potential supply chain, and that is the back end of advanced reactor fuel chains. There are different fuel cycles for many advanced reactors. How do we address finding a proper deep geological repository path, and relevant also to Katie Huff's call, this talk this morning, and Creighton's, and can we possibly at the same time provide fuel stock from many advanced domestic fuel stock from either existing light water fuel or advanced reactor fuel? So that's our portfolio writ large. Oops, I don't know why it's not advancing. But let's just take a couple of those and how they what our developments, how they relate to the supply chain. And this is a Meitner project. I think we're going to hear about this all throughout the future supply chain, and that is additive manufacturing. Here's a case in making spacer grids for actually an existing fleet. And I think the question here is, this would be advantageous to the US supply chain because it could be done domestically, et cetera. However, as we're going to hear in, I think, the next talk by Andrew, but these materials and this manufacturing technology is relatively new to the nuclear industry, and the regulatory hurdles need to be understood. Another Meitner project is the Evinci Microreactor, but it's by Westinghouse. Here I want to point out it's a very different type of reactor. Its heat distribution is done through heat pipes, which is very different than a conventional reactor. We can make these materials here and so on, but they've never been used in this particular case. Even such things as graphites and unique cores and so on. A very important part of our supply chain, and Andrew will speak about this also, that the testing, certification, and qualification of vendors, particularly for new materials, is something that I think has been neglected in this country. And we really have to not only get the manufacturing of new materials and so on, but we need to go through this hurdle if we are going to have a robust supply. Onwards, our final one has some unique challenges in supply chain. First of all, its goal is to minimize the impact of disposal of advanced reactor fuels. And it has some challenges here because first, it needs new innovations and safeguards. But I think most importantly, we would like to co-design and optimize the back end with possibly creating new fuel stocks. And in this case, if we want to reduce proliferation, then that naturally would be uranium and transuranics probably extracted in that particular form. So what's new about the back end that maybe is not in our existing supply chain? I just have a few examples here of onwards projects. The first one on the left shows, and this is another TerraPower funding from OPERA-E, but really to monitor a lot of the advanced reactors, we need new different devices which may have different characteristics that have been implemented in the existing reactor fleet. In the middle, we see an argon electrorefiner module that we're supporting. Again, this is not currently, since we don't reprocess, this is not currently in our supply chain. Again, hopefully can easily be done for the manufacturing. The question is, again, on testing and so on. And finally, if we develop new materials for things like Cermet, for matrices for waste forms, then not only do we need a supply chain for the materials to make them, again, we need to certify the production of these materials. So looking at our portfolio, I try to distill what I think is the good, the bad, and the ugly here of the future supply chain. And the first thing I would say, hurrah for the US. It has tremendous capacity for innovation in nuclear power. It is a wonderful time to be in nuclear. But I want to emphasize that in a lot of our projects, develop and qualify new materials, the radiation and materials testing, both the rad combined with high temperature and so on simultaneously, in particular, is really a bottleneck to rapidly accelerating this. We love new manufacturing techniques, and we know a lot of them are being developed. But here's where I think the supply chain is somewhat jeopardized. We need to rethink the regulatory process because this adds significant commercial risk. And this limits the investment potentially in the players. Right now, we haven't built many nuclear reactors in the US. I think it's really perceived as a relatively small market. And that limits not only investment, but also competition, which we'd like. And of course, the lack of recent deployments, you hear everyone working on reactors, is that even the number of certified vendors with the proper skills and qualifications is a real issue here. So I'll just end with saying that, that's why I see a lot of nuclear power manufacturers looking at, can we really leverage existing qualified COTS material, particularly for the balance of plant? And I think there's significant challenges and promise in the back end, but I think that that's an area that is that really needs to be looked at, since we have not done it in this country for a long time. So I end with that. I look forward to your questions, and thank you for your attention.
Thank you, Bob. Andrew, would you like to fill us in on developments with EPRI?
So I am Andrew Souter. I'm with the Electric Power Research Institute. And as the title slide here indicates, EPRI is celebrating its 50th year this year of existence. Today, I wanted to actually share a lesson from the past, and so I focused on one example, but I think it will speak to some of the key issues that were raised by the earlier panelists. The example is one that had lasting impact on me, so I wanted to share it on with everyone else and pay it forward. First, I wanted to start out with just a brief word about EPRI. EPRI, or Electric Power Research Institute. We were essentially born in a blackout, the Great Northeast Blackout of 1965. Suddenly threw New York City and the Northeast into darkness. and that really caused a lot of concern and action by Congress, which basically came to the utility industry in the United States and said, you either get your act together or we will do it for you. So out of this, EPRI was formed as a collaborative, independent nonprofit center where basically utility companies can pool their money, their resources, and expertise to do collaborative, common need research. EPRI is a nonprofit, and our mission is basically for the public good. And so that pretty much shapes the type of work we do and how we do it. EPRI is now started out in U.S. based, but we are now international. We do have major offices in Palo Alto, California, Charlotte, and Knoxville. And we have major laboratory facilities in Knoxville, Charlotte, and Lenox, Massachusetts. But we do have in-country presence essentially around the world. Our international members include about 40 countries. Our international members comprise about 25% of our research, but over 50% for nuclear now. And in the US, for example, 90% of electricity is generated by EPRI members, and we have 100% of US nuclear operators. But just to kind of close with the introduction here, EPRI has between 75 and 80% of the world's nuclear operators as collaborators in some form or fashion. So it is said that each day, EPRI essentially collects a year's worth of operating experience from around the world. So the topic of the seminar, the conference, is on sustainable nuclear fuel supply chain. And one of the things that came to mind was a great example when I was pursuing accident-tolerant fuel research. That involved essentially developing new fuel forms for current existing operating light water reactors. Well, the lesson that came to me out of that was that even incremental light water reactor fuel changes and evolutions can take decades. So just as an example, current or recent changes of to niobium-based zirconium alloys that are now used in light water reactors, that development of that cladding type, and again, it was just a modification of the composition of the cladding, that spanned about 20 years, give or take, plus or minus 5 years, depending on the supplier manufacturer. And again, this just speaks to the conservative and kind of serial approach that the traditional fuel development testing cycle takes. It typically involves, for example, 3 cycles of irradiation of a lead test assembly in a commercial reactor. And so that can take on the order of just 5 years plus just to get neutrons on the fuel. And then you have to add on, of course, cooling and then getting it into a post-irradiation examination facility, or like a hot cell to do the actual examination. And the assumption in general is that this approach generally assumes that the fuel is pretty much compatible with existing reactor designs to begin with. And so here's one challenge that I think we are prepared to meet, but certainly remains a challenge, is that new reactor designs, such as non-light water reactors, will have environments and advanced fuel designs that represent really dramatic departures from the fuel experience we have to date. Now, more importantly, I think that's often overlooked is if we truly want to have new nuclear reactors online and really producing power and energy to meet our needs and also to help decarbonize economies, we're going to need large-scale deployments, basically fleet-scale deployments. And this is really where the role of adequate material testing infrastructure comes in, because once a new fuel or fuel component enters into service, new data needs always arise. I mean, again, something always goes wrong. So testing, and for example, testing on just the original zircaloy alloy continues after 6 decades of service. I know this because EPRI continues to sponsor work on zircaloy 4 alloys. And again, the image to the left is of an early Oak Ridge report on zircaloy 2 from the 1950s in preparation for deployment in the the nuclear ship Savannah. So I'll just kind of, the tagline here is unanticipated issues will arise, and that can require really aggressive testing campaigns because, again, you have commercially operating plants that need that fuel to perform reliably. Here's the example I mentioned earlier, and I wanted to just give credit to Sam Armayo, who formerly was with GE Nuclear Energy and also was a past chair of the US NRC's ACRS committee. Sam had presented this, and it really had a good, lasting impact on me because of its very specific example. Basically, in the course of light water reactor development in the 70s, a lot of fuel failures were encountered due to what's called pellet cladding interaction. And this occurred in both BWRs as well as pressurized water reactors and even heavy water reactors. But it especially was aggravating for boiling water reactors. Now, the punchline, I'll just get to that, was a successful resolution was reached in only, and I say only, 13 years. Again, this was because they had a very specific problem. You had commercial drivers, you had great leadership, and you had aggressive testing in terms of numbers and severity. In other words, it wasn't just serial testing, it was parallel testing, and access to testing and radiation and post-irradiation facilities were paramount for the success. And the tagline here is General Electric and the other collaborators, DOE, they had access to 6 test reactors simultaneously, essentially, to contribute to the success. And so here's really the meat of my presentation here, and that's kind of a warning that we have a waning global irradiation test infrastructure in the world today. We are adding new facilities, but again, they don't compare to the number that are being decommissioned or have been decommissioned. So these are the 6 facilities that GE and its collaborators had access to solve that problem. 5 out of the 6 reactors are now shut down. And so to me, that's pretty impactful. It means that now there's others available around the world like ATR and others, but again, the fact that 5 of these reactors that were relied upon have shut down and have not really been replaced indicates that we could have an issue here. And I just have them, the GE test reactor Halden, which recently closed in 2018, EVR2, Studsvik R2 reactor in Sweden, the power burst facility at Idaho National Laboratory, and then the nuclear safety research reactor, which is actually still, it's a trigger reactor still operating in Japan. So, closing remarks here. I just wanted to leave a lasting impact with you that to call attention to the first round of nuclear commercialization, that is through generations 1 through 3, really benefited from robust material and field testing infrastructures. And these infrastructures were largely established in the 1950s and 60s. So again, just like our roads and bridges today, we were pretty much relying upon sunk costs and sunk investments from that early period. And you had the large collection in the United States, especially at the Idaho testing site, which is now Idaho National Laboratory, but you also had collection of these around the world with a diverse set of capabilities, neutron energy flux instrumentation, what have you. I would say today, current efforts beyond Generation 3 face a diminished selection of these facilities, especially for neutron irradiation. And I'll point especially to the fast neutron test reactors are especially rare if you want to go to one of those. Previously, you could go to Bor 60 in Russia. Geopolitics obviously has changed that picture over the last many years. And we only have a limited deployment of new facilities, for example, Jules Horowitz in France and Pallas Reactor in the Netherlands. I'll close out by pointing out that I don't see this as really a limitation or challenge for the demonstrations of first-of-a-kind deployments. These are proceeding, and we can find ways to actually get these initial ones off the ground. But true commercialization at the scale that we're talking about needed will require these testing capabilities to address problems as they arise. And so just in closing, we need an adequate testing infrastructure needed in order to support a reinvigorated nuclear industry. irrespective of the particular nuclear technologies that are eventually commercialized. So that's my presentation. Just wanted to start off with those comments. And
thank you. Yeah, thank you, Andrew. Yeah, those great insights, great insights from the panel. Everybody, please feel free to use the Q&A function to submit questions. If I may, I'd like to start off with a sort of basic question for all the panelists. And Creighton, you mentioned that you have foreign supplier partners with TerraPower. Why should a supplier get involved with the nuclear energy industry? Are you finding any resistance that they need to have nuclear grade quality assurance programs or be subjected to them? There may be special warranties. Should suppliers be anxious to get involved with nuclear energy, I guess is the question.
It's a good question. I think that I think that a lot of suppliers are looking at the the potential market opportunities associated with this, not only domestically here in the U.S. But also internationally, because in order to address some of the climate change objectives that parties, that customers and utilities have, I mean, nuclear is going to need to be part of that solution. So there's definitely interest. I think one of the things that is a challenge for a lot of the the suppliers that we work with and are talking to is just some of the investments and the capital outlays that they will need to make in order to support the business case for production. So that's certainly a challenge and a thing that suppliers are interested in trying to ensure happens. I think the other thing that is probably top of mind for a number of suppliers too is the calls for a nuclear renaissance that have happened in the past. They didn't come to full fruition. I think now is the time, though. I mean, when you see it, all the market players that are involved in new nuclear development, and Dr. Huff mentioned several of them, that coupled with the fact that you really have strong bipartisan support right now for, government to be a strong partner to support this development. I think those are the kinds of support to show that a nuclear renaissance at this point is not just a catchphrase.
Andrew, does EPRI have suppliers who are participants with EPRI?
Yes, yeah. Some of our programs are open to vendors, and that's because in many cases, in order to address R&D problems, you actually have to involve them in the program. The program I'm in, Advanced Nuclear Technology, which is our new nuclear technology program, we in fact, have a large number, at least half of our membership are the suppliers, and so they do bring an important perspective. For example, TerraPower has been a long-standing advanced reactor developer, one of the first in our program. So we do seek out to engage that, because until there's customers that are actually operating the plants, right now some of the biggest needs are really coming from the developer and vendor community, and that's really what's different now than in the past. Is once you had a fleet of reactors up and operating, it was pretty much the utilities that were driving a lot of the R&D, and that has changed in recent years, and we've had to adjust to make sure we're hearing from the developer and supply chain community.
Good. And I want to turn to a question. Bob, you raised a significant issue, I thought. Just to kind of frame it out a bit, there have been a lot of advances over the years in things like, I think you mentioned advanced conductors, digital instrumentation and control, even manufacturing techniques and processes, even 3D printing is a manufacturing technique. And I think, and he said there's significant regulatory risk, which caused me to think about the difficulties the Nuclear Regulatory Commission has had for at least 3 decades coming to grips with change from analog to digital INC. For operating reactors, that I can understand that can be a different matter, but for new reactors, there is this regulatory risk. And I guess my question is, what can we do to reduce that risk? Is the NRC involved in any of the ARPA-E programs? So yeah, I think you're on mute, Bob.
That's a great question, and the answer is yes. I mean, we're not a regulatory body, but since we have a strong tech to market focus and we want to get things out the door, we encourage at all stages that our projects interact with the proper regulatory agent. We try to assist and reach out to the NRC because we try to lay the groundwork, I would say, to address specific issues. So for example, in the digital twinning part, there's a lot of work that's going on around the world, including the NRC. And we have active projects in that. So we try to assist our projects with the NRC to frame the issue for us, such that when they go back with a specific question, then hopefully, a lot of the general aspects of how do you regulate a non-static thing, et cetera. What's the difference between using it for operation and maintenance versus some sort of control function? And it's the same with additive manufacturing and so on. There's the test and qualification part, but again, when you go to large scale production that Andrew keeps mentioning, I don't think we have a lot of track record in high performance materials that really know how well, the reproducibility is or what the metrology should be to ensure new manufacturing techniques work it. The last thing I'll say, what ARPA-E tries to do, we have programs in a lot of advanced materials for gas turbines, for fusion. And one thing I'd like to say that, and I know I've talked to Andrew about this, is that a lot of these problems span multiple domains in US R&D. And I think that EPRI, ARPA-E, and so on, we're trying, with the rest of DOE, we're trying to see if we can consolidate that such that not every problem looks unique. And I think that really is an issue. Can we come together and figure out what tests do we need? How do we qualify a material? What does digital mean versus analog? So we're working it, but it's Dan, it's scary to new vendors. That's our experience at ARPA-E, trying to draw people from outside the nuclear field in. You can't give simple answers to those questions. And therefore, new people that aren't used to it, they shy away from it. I think there is an issue there.
Okay, that's a good perspective. Andrew Creighton, would you like to weigh in on that topic about the regulatory risk for some of these innovative manufacturing techniques and new equipment?
Well, I'll just kind of comment on perspective and approach that EPRI takes. We do have a major program in advanced manufacturing methods, and that includes everything additive, but as well as powder metallurgy and electron beam welding and diode laser cladding, et cetera. We also have a major materials focus, so we do work with developers and suppliers to actually develop new alloys, for example. One of our principles, though, is we don't just stop there, is we try to then make sure we build in funding and the resources to then take these new methods and materials through code space. For example, ASME boiler pressure vessel code, because if they're in code space, then it becomes much easier for them to actually be deployed and utilized in a highly regulated environment like nuclear. And so that's one thing we try to do, and I think that's where we dovetail well with ARPA-E, DOE, nuclear energy, and other agencies, is because we really are here as a tech transfer agent for the benefit of our utilities but also the public as well.
Good.
And I was just going to add that when we look at technology risk in connection with interface with the regulatory process, one thing we do is we do a lot of kind of calibration of the regulatory risk associated with introducing further innovations into our Natrium and other reactors, to try and make sure that we get the right balance. We want to innovate. We want to bring new solutions to bear. We also want to be timely when it comes to coming to market. And so there's a constant balance that we're doing. I think another thing that we're looking at carefully at TerraPower is we don't expect that the Natrium demonstration reactor that we license day one will be the same as further developed Natrium commercial reactors. We will continue to innovate and develop the reactor in order to introduce new features to continue to improve its performance and its commercial proposition. A good example of that is in the case of fuel, for example. I mean, we'll start with one type of fuel, a sodium bonded fuel, and we plan to further develop that fuel over time. It would be nice if there were more testing facilities, as Dr. Sauter was referring to, because the options are limited in that space. We'll probably do a lot of that testing within the demonstration reactor itself. But historically, that's definitely been a challenge for us. We've worked with test reactors here in the U.S., but we also have had some materials tested over in Bor 60 in Russia. And as Dr. Sauter was mentioning earlier, that's not a good option from a geopolitical risk standpoint anymore. We really need those capabilities in the U.S. or in other friendly countries where we can easily access them.
Those are great insights. Thank you. It's a key issue. It's not going to go away soon. It's just going to have to be managed for the long term. But moving to the issue of the contracting structures and the difficulties that's been experienced with project execution with new reactor projects around the world, what are some of your thoughts? Maybe start with you, Creighton, on incentivizing all the participants to move in the same direction for project success. What do you think are some of the keys?
Well, I think you mentioned the Olkiluoto project in Finland, and I think that's kind of a classic example of what not to do, which was, a situation where, the owner of the reactor was basically putting back on the, developer and constructor all of the risk associated with the planned development in that case. And I think that trying to align incentives to make sure that project success is the #1 priority is absolutely key for ensuring that you have projects that come in close to being on time and on budget. So I think the contracting structure is very important to align those incentives and not to be unduly punitive, because I'm not sure that at the end of the day, the operators in Finland were really happy with the result that occurred there. I mean, even though they were able to send back all sorts of contract notices and get payment for all sorts of liquidated damages and the like, I mean, it didn't end up being a success for anybody. Maybe maybe some of the lawyers did well in the case, but
There we go.
but other than that, not anybody else. In terms of the objectives, and I think for us, I think when we're looking at contracting structures that we're working with other parties on, that allocation of risk is really important. Another thing that is important in a lot of those negotiations is how we manage intellectual property rights. And that's going to be different depending upon what the parties bring to the table in different circumstances. If you have vendors that bring more background intellectual property to the table, a substantial amount of that, the contract discussions are going to be different, from those situations where, for example, TerraPower is paying for, new greenfield development in some new area as part of enabling the reactor, enabling the supplier to provide the components for the reactor. And so that's another situation where there are opportunities potentially to partner and share upside with parties depending upon what they bring to the table in supply arrangements.
But Andrew, you had mentioned that EPRI was doing work on project execution and lessons learned. Can you say a word about that?
Yeah, because one thing I think is that as engineers and scientists, we often like to focus on the technology itself, especially the nuclear part, because that's pretty cool and interesting, and that's really where a lot of innovation can occur. But as we've, evaluated, and others have as well, what you find out is the root cause of a lot of the issues with nuclear construction is not necessarily the technology part. It's also not the costly part. Most of the cost lies outside of the nuclear island and the balance of plant. I've heard it's been said that you could give away the nuclear island and the balance of plant, and the current going rate is still too much for people to afford. And that's because a lot of the costs are in the construction and maybe the less exciting parts like concrete and rebar. And so one thing we realized, and it was kind of sometimes hard to swallow as an R&D person, the most important aspect for nuclear deployment is project development and execution. And that includes the having the right contractual arrangements, but you need the right people in the right roles, just like on an athletic team or on a theater stage. You need the right players or actors in the right roles in order for the game or the play to go off smoothly. And so that's one thing that we, in the last 2 years, we have stood up an entire research focus area and kind of reorganized our entire research around the phases, going from planning all the way to commissioning and operation, with PDE or project development and execution as being maybe one of the most important parts.
And Dr. Ledoux, I want to turn to the question we talked about. Could you give your views on what are some of the strengths in the U.S. for supply chain for new nuclear?
Well, I think we have a combination of our universities, labs, and private industry. If you give them a problem, I think it's literally the best place in the world to do that. Our government funding is very, government doesn't own anything in the funding. It's very attractive to investors. And we have a mechanism to get, private companies, universities, and so on to work together. So I don't think it's a problem coming up with new ideas, new materials. I think everything that Andrew and Creighton are saying are all relevant. We will make those new innovations. We will come out with them, but we need the full supply chain to join in. And I think that's everything from the regulatory, the testing that we're talking about. It's great companies like TerraPower that are willing to put something out there. But ultimately, I do think the government plays a role here. We certainly do our role of de-risking for industry, new ideas and so on. but I think the commercial reticence to enter this area, given its history and so on, is probably a negative for investment and deployment relative to other industries, in my experience. I came mostly from the commercial market and other things, and this, those same set of circumstances, the negative, the negative history combined with the difficulty of qualifying and so on, it reduces the number of people that can participate. And we have to reverse that also. And I would love to hear if anybody else in the audience has ideas on how government can also help with that. I mean, certainly we want to, but it's a big problem.
As a follow-up, what is your view on how private industries can tap into the expertise at the national labs and that sort of thing?
Oh, I think I think it's almost unlimited. I mean, there is a formal way of doing that. It requires overhead. But as I always tell our projects, if you want to work with the government, get a lawyer who's worked with the US government before, because a lot of the things that seem onerous, if you've never done it, look a lot easier when you really have somebody with experience. But the labs, I think, over the years have been very open to that and welcome participation. I think they gladly want industrial partners for everything. So it's there, it's available.
Andrew?
And I wanted to add to that because one entity that EPRI's been very supportive of, along with NEI, has been GAIN, Gateway for Accelerated Innovation in Nuclear, because it was stood up after White House Summit in 2015 to do just that, which is that I always call them sort of the help desk for the national labs, so that if someone has a problem in industry, they are the interface, because it is awfully hard to understand who to go to and how to access the labs. There's many labs, which is good. There's a lot of people working in the labs, a lot of great resources, but knowing which door to knock on is hard. So I would say the one-stop shop right now is GAIN. I think they've done a great job, and I think will be an important part of this.
If I can just add, Dan,
sure.
OPERE, every project program starts out with a teaming sort of portal. And I would say in nuclear, the average team is probably an industrial partner, because we have cooperative agreements, right, with cost share. So the average team is industrial partner, often a university, and in nuclear, almost always a national lab. So we really try to facilitate that. And if there's any door that we can help open, that's part of our charter, tech to market, working with, and we really try to help.
Well, thank you. Let me, before we run out of time, I want to ask for a quick reaction on a question that came up yesterday. Fiona Riley really emphasized this point, but in the nuclear industry, historically, there may not have been great diversity. She mentioned that she would attend meetings, there'd be 20 people there, and she would be the only woman. Just want to maybe start with Creighton. You have some very strong women who are participating in TerraPower and positions of authority. What can we do to increase diversity in the nuclear industry going forward?
I think thank you for that. I think there's several things. I mean, I think, as you mentioned, having strong women in leadership roles is really important. I mean, the lead of our Natrium project, which is by far our biggest project, Tara Nider, is a fantastic leader, and I think mentor, to women in nuclear. And, similarly, our CFO and Executive Vice President, Marsha Berkey, as well. So I think having those very visible leaders is a big thing. I think it doesn't stop there, though. I mean, I think one thing that, we've sought to do much more is, outreach to universities and to engineering programs in order to try and, cultivate that new talent. And I think that's important. We are, and we're showing good results in terms of, bringing on a more diverse, workforce in order to support our projects, and that goes, across, multiple areas of diversity and inclusion, and I think that's going to be important, long term for for acceptance of nuclear and the industry as a whole, and also just getting the best talent that way.
Yeah, thank you for that, Andrew. How about
So,
with that,
I'll just make the observation. This is, we're not particularly a diverse group here, and always at risk of making comments on these topics. But I would say, thing I noticed is with the advanced reactors and the new this new group of entrepreneurs, I am personally seeing a lot of, young folks, but also very diverse folks that are coming up. A lot of them through the universities. I think the universities are a key part of this, right? Because I think they do a much better job of supporting and encouraging that diversity now compared to the past. I think the other important thing is you do lead by example. So I can't emphasize enough how important it is to see folks in leadership positions that, again, don't look necessarily like this panel. And again, I see that it actually is changing now. And certainly within EPRI, I would say EPRI is an extremely diverse organization. But again, we are an international organization. So by virtue of the way we work, we bring that to the table every day. But I would just sound a positive note is what I'm seeing is at least very diverse, increasingly diverse audiences. And the other thing to do is, no matter who you encounter, give a leg up and encourage folks that you run across, the new folks that have come to the industry.
Yeah, great idea. Bob?
Well, I would say that at OPERE, we can always do better, but the first nuclear fission program director was Rachel Slabaugh. I was the second, and now we have Jen Schaefer. So I really do think that it's changing, like Andrew said. I don't think like OPERE can take, credit for having the great people we have, but having Rachel, Jen, and all the other great, Katie, having those visible leaders that are getting more diversified makes a tremendous difference. And as Andrew has said, if you go into universities now, I have been encouraged because I do think there's definitely more diversity in nuclear than there used to be in the past. And I think wherever we can promote that diversity, particularly through leadership, setting examples is very important. But I still don't think we're doing enough in this country. STEM is horribly underrepresented by women to this day. And I think that we have to do more. But it's at least in nuclear, I think it is getting better.
Thank you. Yeah, we don't have time to go into it now, but the U.S. government, DOE, have the mentor-protege type of programs and things like that, where companies can team up with small and minority-owned, women-owned businesses and things like that. So I think we have to close out, Donna, and I just want to, first of all, thank our panelists for the great discussion. As you can see, they have tremendous insights. And I really thank Donna and her team for bringing together a panel like this to discuss such an important topic.
I want to extend my thanks to each of you. This has really just been absolutely fascinating, and I appreciate the time and effort you've put into it. For our audience, we will be moving on next. This webinar will end. You will log on again, and we will next be hearing from Dr. Ben Cross. So please, we'll see you shortly. Thank you all.
Thank you.
Thank you, everyone.
Appreciate
Appreciate it.
Bye.